As promised in the last video, we're going to start talking about the types of symmetry that a non-zero function could have. So I've just got two examples up here. Y equals x squared, our squaring function, is an example of something that's symmetric about the y-axis. And I can basically see if I have a point here, x, y, its mirror image on the other side of the y-axis has the same y value, but the opposite x value. Okay. And then y equals x cubed, that's an example of a function that's symmetric about the origin. Remember, we also call that rotational symmetry, and it's maybe a little bit easier to see if you actually just take the graph and flip it upside down. But basically we're saying if I've got a point here, x, y, its mirror image point would have both the opposite x and the opposite y value. Now, when we're just working with equations that could be, but could also not be, functions, we had to check for these types of symmetry separately. To check for symmetry about the y-axis, we replaced x with the opposite of x and saw if we got the same equation. To check for symmetry about the origin, we replaced both x and y with their opposites to see if it would simplify to the same equation. What's nice about functions is if I use function notation, one test will test for both types of symmetry. Let's see how that works. I want to remember that a fancy name for y would be f of x. That just means the y value I get when I plug in a particular value of x. So here, this y value would be f of x, okay, because that's what I plugged in to get it. Using function notation, this y value would be f of the opposite of x, because that was the input I plugged in to get this. But notice, they're the same y values. So if this y is equal to that y, that's basically saying that f of the opposite of x is the same as f of x. Now if I think about what that's saying if I plug in the opposite number as my input, I'm going to get out the same number for my output. So this is opposite input, same output. Now that nicely summarizes what happens with the squaring function. I know if I plug in 2 and I square it, I'm going to get out 4. Now what happens if I plug in the opposite of 2? Well, if I plug in the opposite of 2 and square it, I'm also going to get 4. So opposite inputs lead to the same output. Now over here, if I use function notation for this, so I say f of x for this function is x cubed, then I can label my y values using that function notation. So this y value would be f of the input x. This y value would be f of the input opposite of x, because that's what I plugged in to get this. But notice here we're saying these y values are opposites of each other. So what this is saying is that f of the opposite of x is the opposite of f of x. Opposite inputs give me opposite outputs. And that does summarize very nicely what happens with the cubing function. I know if I plug in 2 and I cube it, I'm going to get 8. If I plug in the opposite of 2, I'm going to get the opposite of 8. Okay. So, with this function that was symmetric about the y-axis, opposite input gave me the same output. With the function that's symmetric about the origin, opposite input gives me the opposite output. Okay. So I can basically test for both types of symmetry if I simply evaluate my function f at the opposite of x. If I get the same thing as the original function, then I've got a symmetry about the y-axis. If I get the opposite thing, I've got symmetry about the origin. And we actually name these functions, and we name them based off of these examples, essentially. We say f of x is even if it has the same type of symmetry as even power functions do. All even power functions are going to have symmetry about the y-axis. So f of x is even if it has this property, that the opposite input gives me the same output, and that means that the graph is symmetric about the y-axis. And then we say f of x is odd if it has the same symmetry as all odd power functions do. Any odd power function is going to have this same type of symmetry about the origin. So f of x will be odd if the opposite input gives me the opposite output, and if that's the case, the graph is symmetric about the origin, or has this rotational symmetry. And of course, it's entirely possible for a function to be neither even nor odd. I could have a function that looked like so. That's not symmetric about, I'm sorry, we can't go straight up. Didn't mean to go straight up there. All right, I could have a function that looks like so. That doesn't have symmetry about the y-axis. It doesn't have symmetry about the origin. That would be neither even nor odd. So I can test for symmetry by simply seeing what happens when I plug in the opposite input. So let's just try an example together, and then I'll give you a few to try on your own. Let's let f of x equal x plus x to the fifth, and let's let g of x equal 2 plus x. Okay, and I want to see whether these functions are even, odd, or neither. Okay, so I'm going to look at what is f of the opposite of x. So that means I'm replacing all of the x's with the opposite of x. So we're going to have the opposite of x plus the opposite of x to the fifth. Now, I'm not doing anything to this one, so that's just the opposite of x. Taking the fifth power, that's going to preserve that negative sign. So this is going to become the opposite of x to the fifth. Now you'll notice that gives me a negative sign in front of both terms. So I could factor out that negative, and if I do, I see, oh, I'm getting the opposite of x plus x to the fifth, but that's the opposite of f of x. So this function, opposite input, gave me opposite output, so this function is odd. Now you might notice that the function was actually a sum of two odd powers, because x is just x to the first, and x to the fifth, obviously that's the fifth power. So it was a sum of two odd powers, and that will always be odd. Let's take a look at g of x, which is 2 plus x. If I look at g of negative x, I'm replacing x with the opposite of x. So that would be 2 plus the opposite of x. That would just become 2 minus x. That's not the same as this, and that's not the opposite either, because these terms are opposites, but these terms are the same. I need every term to either be exactly the same or exactly the opposite. And if I have a mix and a match, this one is going to be neither. So notice, even though that x is an odd power, adding that constant to it made it not an odd function. That's because a constant really counts as an even power, because 2 is the same as 2 copies of x to the 0. Remember, anything to the 0 power is just 1. Okay, so constants count as even powers. So I can add a constant to something like x squared, and that'll still give me an even function, but adding a constant to an odd power is going to mean that I don't get something that's either even or odd. I'm going to get something that has neither type of symmetry. All right, I'm just going to put a few formulas up on the board for you folks to try. I want you to tell me whether these functions are even, odd, or neither. Okay, so y equals the absolute value of x plus 3. I'm sorry, let me use function notation. Let's call that f of x equals the absolute value of x plus 3. Let's let g of x be the absolute value of x plus 3. Notice the difference. Here I'm taking the absolute value and then adding 3. Here I'm adding 3 to the absolute value and then taking the absolute value. And let's let h of x equal x squared minus 2x cubed. So for each of these functions, plug in the opposite input. If you get the same output, you know it's even. If you get the opposite output, you know it's odd. And if you get something that's neither exactly the same nor exactly the opposite, you would have to say it's neither. So try those problems before you tune in to the next video, and then we'll check those together.